Ladies, gentlemen, compliments of the season. Thank you all very much indeed for coming out tonight for this, our final lecture in the SLAC Public Lecture Series of 2004. For us, it's been a great experience. These lectures, it's new. It's the first year we've done these, and each lecture has been a full house, and I thank all of you for making the effort to come. It makes us happy, it makes us feel good. It's worth doing it. Tonight we have a great lecture ahead of us. Tonight's lecturer is Professor Joachim Stohr, who is one of the most distinguished scientists in the world in the field of synchrotron radiation. Joe has had a pretty nomadic career. He's been around. He did his master's degree, I think, in Washington State. He was a Fulbright scholar up there. He then went to Germany, to Munich, to do his doctorate. He then came back to Berkeley to do postdoctoral work. He then came here for a few years. He then left here and went to Exxon. After Exxon, he spent 10 years, I believe, working with IBM. And he's now back here again, and I really hope he stays here. Joe, get a hint. Joe's perhaps his most famous contribution to science, in fact, we all see around us all the time. Flat screens on computers, flat screens everywhere now are something which Joe played a very leading part in developing the technology to allow us to have this kind of a screen rather than having a big tube to carry around with us. A couple of protocol issues. Can you keep your questions until the end? That Joe will run through his talk at high speed and leave plenty of quiet time at the end for questions. And then when the talk is finished, I'd invite you all to go outside. We have cookies and drinks, and also we have other scientists from SLAC who will be there to also answer any questions you might have. You can recognize them by their scientist look, and but we've also helped you by making them wear a black SLAC baseball cap. So feel free to go up with them and ask them any kind of question, but questions about science are probably better. Before we start, and with Joe's permission, I'd like to do a bit of advertising, in fact, for another talk. I'll have to start shouting. This is a talk tomorrow night down on Stanford campus. I'll just put this up so you can see it. This is a talk by André Linde. André is, again, one of the great cosmologists of our time. He was instrumental in thinking up the idea of inflation, how our universe reacted immediately after the Big Bang. He's giving a talk at the Kresge Auditorium down on campus at 8 o'clock tomorrow night on the origin and fate of the universe, which is a pretty all-encompassing talk. I strongly advise you, if you've got the time, to go. It would be fantastic. However, tonight we also have a wonderful talk, which has a title more like a film, a movie, than actually a science talk. It's called Physical Attraction, the mysteries of magnetism. I'd like you to welcome Joe.
Well, thank you all for coming. As Neil said, it's good for a speaker to see a full house. It would be embarrassing to have one or two people, and especially people in the first row have to stay awake. Let me start out by telling you about the next lecture. It's coming up February 22nd. It's called Uncertainty, Quantum Patterns, and the Universe. Everything you ever wanted to know. By Michael Peskin of SLAC. For those of you who are interested in learning more about upcoming lectures, to keep informed, you can go to this website. And if you want to have a tour of SLAC, They are very popular. Go to the web and register. So, now to the mysteries of magnetism. I wonder why you came, whether you want to know about magnetism or physical attraction. Anyway, I think the talk is more about magnetism, but Neil thought of this catchy title. So, magnetism in humans. Let me I guess you all know magnetic attraction, here seen by Elvis. You have probably also heard the term animal magnetism. It became very popular in the 1800s. And I'll come back to that a little bit later. And there's some remnants today. There's still people walking around with magnetic bracelets because they believe they heal. But from myth to science. So if a person walked down the street and you asked, what comes to mind when you think about magnetic objects? I actually tried that on a few people. And so, of course, a magnet comes to mind. Refrigerator magnets come to mind. A compass, of course, everybody associates that with magnetism. And some more sophisticated people also know about the detailed magnetic field of the Earth. So this is what a common person would kind of think about. Now, if you ask somebody at SLAC, a scientist, he would have some ideas that were quite different. Some magnets would come to mind. As you may know, if you went to the previous lectures, at SLAC we have a lot of accelerators, and these magnets are very useful because they guide the beam in our accelerators. Some people would think of levitation trains. They are very, some models being built, some tests done, especially in China. Companies in Germany and Japan are building such trains. MRI, some of you may have had an MRI looking into your body. So this all has to do with magnetism. And some of you may not know this, but in your computers, magnetism plays a big role. In fact, I'm going to tell you a lot about that today. So let me give you a quick overview of the talk. I'll start with a historical perspective, what I call the spin on magnetism. Magnetism today is my next section. I'll tell you how in the high-tech society we use magnetism, and you will probably be very surprised to see some of the things. And then I'll tell you a glimpse of the future. I'll tell you about the ultra-small and the ultra-fast. So let's start with a historical perspective. How did the term magnetism get started? Well, we don't really know for sure. But legend has it that a shepherd by the name of Magnus found walking around somewhere while herding his sheep that his cane that had an iron tip on it was attracted to rocks. This supposedly happened in old Greece. But it's more probable that the name comes from the city of Magnesia, which belonged to the Greek Empire at the time. It's in modern Turkey. And this city is well known to be surrounded by magnetic rocks. The history was documented by students of a person called Thales of Miletus, who lived in old Greece. Doesn't quite know when he lived, approximately this time. All of his writings basically disappeared, but his students took notes, and they attributed the first mention of the word magnetism to him. And Thales was said to have used magnetism as the attraction of iron, which existed at the time, by lodestone. Lodestone is a name that later was used in navigation, lead stone, compass, but it's typically called lodestone. And it's a mineral, a naturally occurring mineral shown here as a little rock sample. So naturally, when you have a piece of iron and you bring it in contact by lodestone, it gets attracted. So that was the first description. A few hundred years later, we're still before Christ, as you see here. The Chinese developed the technology. They really used magnetism for the first time, to our knowledge. And they carved a spoon, shown here, out of lodestone, same kind of rock, after a certain recipe. They did it always the same way. Then they placed this spoon on a non-magnetic plate, just a plate of bronze, and the pointer, this handle, always pointed in a direction because they did it always the same way. And that direction was south. Now, you may think that these spoons were used as for navigation, but that's not true. They were actually used as direction pointers because the Chinese believe in living with a harmony of the forces of nature. And even today, you probably have heard the term feng shui. I hope I pronounced that right. I didn't ask my Chinese students whether I said this right. But people still in California, and especially in the San Francisco Bay Area, often arrange their furniture to make the flow of nature bring them wealth and prosperity. So this is the same thing. The Chinese aligned buildings because it gave them a direction pointer. So they aligned the buildings that way. They put the furniture in the buildings according to this scheme. It wasn't until much later, in the 11th or 12th century, that the Chinese actually used it for navigation. And very soon afterwards, it was used, came to Europe, and it was then used as a ship's compass. Now, the person who really explained why you can use it as a compass is William Gilbert, an Englishman that wrote a very famous book at the time, around 1600, that basically summarized the knowledge that was available on magnetism. It basically was magnetism of rocks and so on, and how they oriented themselves in the field of the Earth. And he built a whole philosophy that the Earth itself was a big magnet. And therefore, he could explain that the compass needle always pointed a certain direction. Now, how the Earth's magnetic field really comes about is still a mystery. This is very surprising. It is actually, everybody knows that the Earth has various shells, and the most important part of the Earth is a liquid iron core. We know that iron is magnetic, but it's not the magnetism of iron, but that it is a liquid and that currents flow in this liquid core. And they act as if there was a magnet in the Earth. And therefore you have field lines that go across the surface of the Earth. And if you place a little magnet, a bar magnet, or a compass needle, it's the same thing, into just put it on a table or so, it points toward the north-south direction. By convention, people then paint the part of the compass needle that points north red. Now, north, of course, we can tell north by the stars. But we can also, there's also something called the magnetic North Pole. And that, of course, makes that's what the compass needle points to. Now, it's actually quite interesting that if you use a picture that is all consistent, that means the magnet aligns this way, that the North Pole points north, and you were to assume that the Earth's magnetic field arose from a bar magnet inside the Earth, the North Pole would actually be a South Pole. But it really doesn't matter, because every 500,000 years, the Earth's magnetic field switches. Now, fortunately, not within our lifetime. But there are indications, and some people believe, that we are in the middle of such a switch. All right. So after 1600, we go on to 1800. And here we run again into this character Mesmer that everybody knows, because mesmerizing is a famous word in the English language. In fact, he became so famous because of magnetism and because of animal magnetism, that his name remained a word in the English language. That is, doesn't happen to too many people. In fact, he was so famous that this picture here was born in Germany, Austria, Switzerland, somewhere on the border, because the boundaries have changed, so people, I don't really know, somewhere at the border, so that's why I wrote this down here. And this is a German picture. It says, father of magnetism. I mean, we of course know that Mesmer wasn't the father of magnetism, but he played such an important role that some people associated him with the father of magnetism. So what he claimed is that he had healing powers and that the body had magnetic fluids in it, and sometimes when the flow of energy or magnetic fluids got stuck, he could undo it. And he could therefore heal patients. Now, around 1800, around the same time, some philosophers, mind you, that the science of magnetism is still at an infancy stage. We're still talking about magnetism and rocks and stuff like that, so people didn't really know what it was. And one of the great German writers and philosophers, Goethe, around 1800, had the famous saying, "The mystery of magnetism, explain that to me. No greater mystery except love and hate." And he built a whole philosophy on this. He said, magnetism is so fundamental, we cannot explain it. It's just there, and we have to accept it. In fact, this whole philosophy is called natural philosophy today, and it's based on the fact that two opposites make a whole. For example, love and hate, black and white, north and south, plus and minus, and so on. And it's quite funny, because even today, this actually contains a very important modern element that is very much what we know today, namely that magnetism always comes as north and south poles. There are no isolated poles. You can have plus charge and minus charge, but you cannot have only a north pole or only a south pole. So it really comes together. Now, there was a big breakthrough around 1819. And we finally get away from magnetism associated with rocks, because this really was the beginning of a revolution. And it was started by a person by the name of Ørsted. He was Danish. He lived, as shown here. And here is a picture of him showing his experiment. You see the little compass needle? He had a voltaic element here that could make a current run through a wire. And he could just turn this wire around with the current flowing through it, and he would observe certain things. For example, when the current flows, the compass needle that was originally oriented in one direction turns around. And if you do it the other way, if the current flows the other direction, the compass needle turns exactly opposite. And it turns perpendicular to the flow of electricity. Now, for the first time, therefore, people saw that you can influence magnetism with something that is up to man. We can put a current through a wire, and we get something magnetic. Now, the explanation was soon after given by some French scientists by the name of Ampère and Biot-Savart, and they explained this in a way that when you have a current, it actually creates a magnetic field. And so when the current flows in one direction, it has a circular magnetic field around it, and the sense of the rotation depends on the current flow. It is actually a right-hand rule. If the current flows along the thumb, the magnetic field lines go like the fingers. That's what we use today to explain it to students. And so if you turn the current direction around, of course, the field turns around, and the field just takes the compass needle with it. Now you may think, well, so what? This is not, it's kind of nice, but who cares? My computer doesn't care, I guess. These animations are really tricky because you have to, there we go. All right, so now I tell you why that is important. It was only 10 years or so later that Faraday really realized, and he did experiments that continued what Ørsted had done, that Ørsted had stumbled onto something that was fantastic. It was, in fact, the foundation of the industrial society as we know it today, because you all know that electricity is very important. What Faraday realized, he was an Englishman, that if you have a magnet, like Ørsted, you have a wire, but you don't just hold the wire still, but you move the wire or you move the magnet. So you add one more element to it, motion. You create electricity. So an electric generator today, as we know it, all of our electricity that we have is created from very simple things. You have a magnet, you have a wire, and then you have motion. I'll tell you in a little bit where the motion comes from. That gives you electricity. We can turn this around. We just change electricity on motion, and that's an electric motor. Because when we have a magnet, a wire, and send electricity to the wire will move. And here is an illustration of how this works. We just have a magnet that has a magnetic field. We have a wire that has a coil. And so if you crank this, of course today that is done by turbines or something like that that turn something around, then in this wire a voltage is induced. And if you hook it up to a voltmeter here, you see that you can get electricity. The other way around is if you have a current source and send current through the wire while it's in there, the wire will start moving and it will start rotating. And that's an electric motor. It's all the same stuff. So why is this so important? Electricity is big business. So, I mean, these numbers may not mean anything to you. The US electricity retail sales, all the electricity of producing it, selling it to one power company, then selling it to the consumer and so on, is $3,500 billion a year, or that in another way of saying that, it's 3.5 trillion. So what is 3.5 trillion? All right, let's put it in perspective. The total goods that are produced in the United States, which is the gross domestic product, is 10.9 trillion. It's only a factor of 3 times larger than the total electricity money that is made. So that's a good business to be in. And here are the 7 largest economically most powerful nations in the world. And you could see it really goes with the production and consumption of electricity. In fact, the money that is made in the US with electricity is larger than the gross domestic product of any European nation. It's just amazing. So how does it work? It's just very simple, just like Faraday did. All we have to do is we have a magnet, we have a wire, and then we have to create motion by a turbine. And the motion is turned into electricity. So we can have a water wheel or a dam, and the water drives a turbine, rotates it around, we create electricity. We can have nuclear energy, which we use to heat water. The water goes into steam, it drives a turbine. Or we burn fuel, either coal, oil, or gas. We create hot gases that drives a turbine. That's how we create electricity. About half of the US energy is consumed as electricity. So it was an important discovery. All right. Now, Faraday was a whiz. He was probably the greatest experimental physicist of the 19th century. And he didn't stop there. He did an experiment that also is very important. And because he discovered the connection of magnetism and light. And the experiment goes like this. It was known at the time that if you take certain crystals, which I call polarizers, and you orient them a certain way, and then you take a second crystal and you orient them exactly 90 degrees opposite, that no light goes through. So if you have a screen here, you wouldn't see any light. Okay? So Faraday then put a magnetic glass in the way and wound a coil around it, and the glass was just transmissive. So the light beam just went through the glass, but it was still stopped, just as if it wasn't there. But now, he put some electricity through it. Now watch what happens. You have to watch now what happens here and here. Light. So when you fire up this magnet and produce electricity in this crystal, light comes through. So the light that was originally stopped here now can go through. So this was clear that magnetism affects light. Now that was really, he probably scratched his head when he saw that, because this is pretty complicated. So what it meant is that light must have a magnetic component. All right. So, and Faraday really didn't figure it out, what it was. It was an experimental observation. He was an experimental scientist. But then came along Maxwell. He was a Scotsman. And while Faraday was maybe the greatest experimental physicist in the 19th century, Maxwell arguably would be called the greatest theoretical physicist. And he put it all together. He wrote down these simple equations that the beauty is in their simplicity. And I mean, if you, I guess many of you know that Einstein wrote some very beautiful equations, E equals mc squared. And this kind of has a sense of simplicity to it. It's just so beautiful, and it has everything in it. It has all the connection between electricity and magnetism, and I don't expect you to understand them. But I just want to point out that these equations combine everything. They explain everything. And they explain that light is, in fact, an electromagnetic wave. In fact, these equations still, blow people's mind today. When I was an undergraduate, and somebody wrote those down, I didn't know what they meant. That was just amazing to me. And in fact, I wasn't the only one. Ludwig Boltzmann was one of the greatest physicists in Germany at the time. And he said, was it a god who wrote those symbols unveiling the forces of nature? So this was really something. I mean, these equations were so powerful. And they are still, of course, in every textbook today. Now, what does it mean? Equations don't mean anything to you, but this may mean something to you. You all know TV. You all know radio, radar, microwaves, light, X-rays, and some of you have probably heard of gamma rays. It's all the same stuff. Now, that's pretty amazing. The only thing that differs is that they all waves, and it's the wavelength, which is kind of, if you think of a wave going this way, it's the distance between two crests of a wave. So it's this distance. This distance is very long up here, and it's very short down here. Only the wavelength is different, and all electromagnetic waves have an electric component that swings in one direction, and a magnetic component that swings in a perpendicular direction. So when we talk today about wireless communication at the speed of light, this is really what we mean. The waves that we use, the radio waves, microwaves, infrared, ultraviolet, X-rays, are all the same stuff. And here is an illustration. Radio waves have the size of a house or half a house and a big antenna on top of your house. Microwaves, of course, have a wavelength. This is the wavelength here, between a baseball and a period somewhere. It's a range. Visible light is up here. This is what we call light. And then as we go shorter wavelengths, the wavelength is the size of an atom if we go to X-rays. Now there's something very important in all of this, and that is that with your own eyes, and we will come back to that in a little bit, with your own eyes, you can only see things that are larger than the wavelength of visible light. That means you can only see this world. This is the invisible world, where we need special microscopes to see it, because the wavelength of those rays are smaller, and they are the size of these small objects. We will come back to that. So it is clear that it is hard to imagine today our society without wireless technology. Right? We all take it for granted. But it's all an electromagnetic phenomenon. Now, in the 1920s, there was another big event. And it all happened in a very compact period of only about 7 years. It was just by accident. A lot of things came together. And the history of physics and the history of magnetism, it was a big jump. There are various concepts, and I don't expect you to understand them, but I will explain them to you in my next view graph. I'm just going to put some terms down here. What was discovered is the concept of spin. What was discovered is what we call today quantum theory. What was discovered is the origin of magnetism in magnetic materials. And these are the key people that participated in these discoveries. One really important concept that arose during that time was the concept of the electron spin. Now, we could start to have an idea if we had a magnetic material and we broke it down in smaller and smaller parts. Ultimately, we would find the building stones of magnetism. And this is the building stone of magnetism, spins that are associated with electrons. I'll come back to that. So the concept of the spin, because it is a quantum phenomenon, is still very mysterious. I'll just give you an example. The spin you can think of as an arrow, for lack of better things to imagine. It's an arrow. It can point in all kinds of directions. But when we measure it in a specific geometry, it always is up or down relative to what we call a quantization axis. And this is very difficult to understand. So what we talk about spins is up and down spins. So with this concept of the spin, I can take you a step further. So if we now look into a magnet and ask, what is inside a magnet? What makes this magnet magnetic? We can break it down. And today, of course, we could look into a magnet because we have methods to do that. If you were at Herman Winnick's talk, first talk in the series, you would have heard that X-rays can see atoms. So if you looked inside a magnet, we would see atoms. And if you had if you could sense the spin, you would see that in a magnet, the atoms all have moments, magnetic moments, that are all aligned in one direction. That's why a magnetic field has a very well-defined direction. So a magnet consists of aligned magnetic atoms, and now we could look inside an atom, and then we come to this mysterious concept of the spin. Because the electrons that whiz around the nucleus of the atom have spins associated with them, and if you don't have an equal number of up and down spins, then there's something left over, and that makes a magnetic moment. So we have a very simple way then to say this. A magnet is an arrangement of atoms with aligned spins. That's really what we today associate with a magnet. So that brings me to magnetism today, the high-tech society. Now, I've told you that electricity and wireless is very important in our society, but we're going to just take that for granted right now. And now we're going to look at something more interesting, namely what people that do magnetism research today are really working on. People like me, for example. So, many of you probably have heard that magnetism has something to do with computers, but we live in Silicon Valley, and computer one can think of as having two important parts to them. One we call memory. When you do pictures or word processing or something like that, you always have power on, and the computer does operations and forms one image out of another one and stuff like that. That is all done in memory. We call it, it's done on the chip or random access memory. So that's actually why Silicon Valley got its name, because RAM, or the chip technology, today these are made out of silicon. And the ones and the zeros that are used for a computer to talk are just plus and minus charges on a silicon chip. Okay? Now, in the future, things may be different. But before we come to that, there's another part to computers. You all know that. Before you turn your computer off, you better save things, because otherwise they are lost. Because whatever is in the memory here, when the power goes, your information goes. And I'm sure you have all lost some information on computers. So that's why you write things to a disk. And the disk looks like this. It's just like a little disk that rotates around. And then, if you look in more detail, this little head here is a very complicated thing. And we will now look at what goes on here. The zeros and ones, when you store things or you write it on a disk, are just small magnetic areas where the magnetization or the direction of the little magnets is either one way or another way. That's how it works. And that's when you turn the power off, the magnets stay. If you turn the power off, the plus and the minus charge goes, but the magnets stay. That's why it works. So let's take a look at that. Here is a movie that was given to me by a friend from Hitachi, which is a big company that bought the business from IBM. And here is the little bits, the ones and the zeros. Here are the elements that change or read the ones and the zeros. And now we're going to see how this process works. So the recording process, you send a current through a wire. You create a magnetic field. The magnetic field turns the little regions of the magnetization around and change a 0 into a 1 or a 1 into a 0. So you fire up this little coil, and it passes the magnetic flux down here, and it switches the bits around. Okay? So now you read it. You have written the bits, and now you use a sensor, which is a very complicated thing. I can't go into details. And now you want to read back the zeros and the ones. And if you look carefully, it doesn't, these bits are not always 0, 1, 0, 1, 0, 1, because they go 1, 0, 0, 1, 0, 1, 1, 1, 1, 1, 0, because 8 of these bits is a byte, and they have the information in it, right? So every byte is different. So you can read all this information back. So let me tell you a little bit about the data storage industry. It's a $53 billion worldwide business, and it just so happens that Silicon Valley is called Silicon Valley. It could also be called Magnetic Recording Valley or Magnetic Valley, because all this technology was developed right here. And today, all the people that work in all the different storage companies, they all started at IBM, most of them. And here, this is why. IBM in 1956 built the first data storage system. Now that doesn't look anything like the little disk drive in your computer, but look at this monster here. A stack of 50 giant disks, 24-inch in diameter, and they made a lot of money in those days. They rented out their storage capacity for $35,000 a year to their customers. So IBM did really well those days. Now, if we look at this today, and if you look into your laptop, you see a little disk. I mean, this is my laptop. You can imagine how small this is, right? And look at the numbers here. 4 megabytes, 200,000 megabytes, $90. Now, that may not impress you, but now I'm going to impress you, because one of my students told me this, and I first couldn't believe it. Now, many of you may have an iPod at home. I don't, but my students do. So here's an iPod, an Apple iPod, and it has a little magnetic recording device in it. It is a 40 gigabyte hard drive. This is the best of the industry. This is a moderately good one, right? And so you ask, how many songs does this little iPod hold? 10,000 songs, right? So if you do a quick math, then you see it takes 40 gigabytes to hold 10,000 songs, and those of you that are fast in math can now calculate how many songs you can hold on this stack here, right? I'll give you the answer. That's pretty amazing. All right, on we go. So to give you a feeling, a little bit of a feeling, I'm running out of time, to give you a little bit of feeling of what it means to record data, I want to get another concept across. Namely, this all looks beautiful in the movie. The disk spins underneath this magnetic recording head, just like a record player. All right, so what? But I'll show you what is special about this. An old record player like here, 33 RPMs, for the record to turn around once takes about 1 second. Okay? So in a computer hard drive, the best drives today turn around with 15,000 RPMs. That corresponds to a speed of 1,000 miles per hour. Jumbo jet is about 500 or so. Now you can imagine how flat that disk has to be, because if there's any bump in there at that speed, that's called a head crash. Those actually happen. But the technology is so good that it doesn't happen very often. So how long does it take for the disk to spin once around? It takes 4,000ths of a second, what scientists call 4 milliseconds for one round. But that's not all. So that just means high speed. Now, you have to ask, how many of these ones and zeros bits go around one of those round? It turns out that in a 2-inch diameter disk, you can have 1 million of these little ones and zeros going around. And now if you calculate of how fast does it take for one bit to whiz underneath this magnetic recording head, you come up with incredible speeds. It takes 4 billionths of a second. This is really, really fast. So this technology is really amazing. The bits are incredibly small. I'll tell you a little bit how small they really are. And the writing and reading speeds are phenomenal. Here is a picture that supposed to give you an idea of how small these bits really are, the little ones and the zeros. I hope you understand the view graph. Well, let me explain it to you. We know that in nature, we can see things like a flea or a human hair, or if we use a microscope, we can actually see our blood cells. And here are the distances. Fortunately, we can't use inches, but scientists use metric units. So a flea is a millimeter. Human hair is here 50 micrometer or so. That gives you, and here is the wavelength of visible light. So visible light can see all this, but it cannot see this. So on the technology side, somebody manufactures pinheads that are a millimeter size of a flea. And you also have probably at home CDs. And the CD tracks are just little indentations in a flat area. They are of this size. Now, where we are today in the recording bits in computers is down into what we call the nano world. You may have all heard nanoscience. This is so small that you can't see it anymore by human eye. So we need, let's say, an X-ray microscope or an electron microscope or something like that to really see it. On the biology side, objects that are very small are like a virus or a DNA helix or a water molecule or all the way down to the size of an atom. We know that we are here and that ultimately as we make these bits smaller, and you all know that you want to shrink things, you want to fit more bits on a disk, so the industry wants to make them smaller and smaller and smaller, that we're going to run into a limit. That limit is actually quite well understood because we have very powerful methods to really see what small objects are. We have a lot of sophisticated microscopes. And we know that if you make a little magnetic area below a certain size limit, the magnetization or the spins are not all aligned anymore and make a nice 1 or 0, but they're all over the place. They just wiggle around too much. So the bit isn't stable anymore. So we know where this limit is. I'll come back to that. But we can see it today. This is just an illustration. In fact, it's a beautiful example. Hermann Winick in his first lecture showed the discovery by the German scientist Röntgen in 1895. And of course, you all go to the doctor, and Röntgen rays are called X-rays in English. And so you can take body pictures like here. This is probably Röntgen's, the hand of Röntgen's wife. It's a picture taken by him. And just to show you how far X-rays have come, because they are electromagnetic waves, X-rays can not only see bone, because they get absorbed more than by tissue, but X-rays, because they're electromagnetic, they can also see magnetic objects. And this is the first image taken with X-rays of bits. Magnetic recording disk, at the time recorded by IBM. The black area is a 0 bit. The magnetization points this way. The white a bit like that. This was done here at SSRL or SLAC in 1993, 100 years later. But the scale is impressive. This is a hand. This we can't see anymore. We need X-rays. So now I'm going to talk about a glimpse of the future. We have a pretty good idea, as I told you, of where the limits are in size. But there is another important factor. I mean, you all know you want smaller and you want faster, right? Because you're all impatient. You don't want to wait. So we want to read these bits and do our operations in the computer as fast as we possibly can. Now, we have talked about size. Now we're going to talk about time. How fast can we do things? And where is there a speed limit? Now, the problem is that today, when people at Hitachi or in the research labs explore how fast they can record things, and that they want to write 0 and 1 bits very reliably. They have to do it 1 billion times. There can be no errors. Otherwise, when you have your computer at home, it would be a mess. So it has to be a very reliable process. And you all use a kind of relatively straightforward technology discovered by Ørsted. You send a current through a wire. It has a magnetic field around it, and the magnetic field is used to switch the bits. And that is a magnetic recording head. You wind a coil, and the coil makes a magnetic field, and that switches the bits. Now, today, we can only do that so fast. In fact, if they knew how to do it faster, your computers would run faster, right? But so the big question is, the million-dollar question is, how much faster can we go? Is there a fundamental limit that we don't know about where we really run out of steam? So, as I said, with this method, sending a current through a wire, we can only explore certain times. This time scale so far doesn't mean anything to you. I'll come back to that, right? So we want to see if we go faster, what happens. And we can't go faster this way. So here is the ultra-fast world. How fast is fast? Actually, this may not mean much to you. It means a lot to biologists, because how the proteins and the big molecules in our body change shape and stuff is a very important part of functions going on in your body. We know that in nature, we also have a sense of what this time scale is. This is all foreign to you, I'm sure. But we know that if you have an atom in a crystal, that it doesn't stand still. It just wiggles around. And it wiggles around with incredibly fast. In fact, if you take an atom as a nucleus and an electron that whizzes around an atom, this electron whizzes around with incredible speed. And that is down here. I can just call that kind of the limit, how fast an electron whizzes around an atom. So if we ask, how fast are we relative to these processes that we know exist in nature, in technology? Now, it's difficult to kind of get a feeling for this. But here is one way, maybe, that you can relate to. If you took a high-powered rifle and you put an apple there and you shot a bullet through an apple, and you can't see the bullet here. No, you can't see it. This is the bullet. And you would take a picture with the best camera you could find, the fastest camera, because you have to have very fast shutter speed to catch the exploding apple and the bullet at the same time. That is what let's just call it 1 microsecond. Okay? Computer technology, the reading and the writing of the bits, is 1,000 times faster. So that already gives you an idea. That is pretty fast, right? But we want to go here. How fast can we go, right? So we here wanted to, at SLAC, we wanted to explore the technology void. Is there a speed limit? But how can we explore this? Now, it turns out there are ways. And the breakthrough idea was actually one of my colleagues. In fact, we're writing a book together on magnetism. Hans Siegmann, he was a professor in Europe at the ETH, one of the world leading scientists in magnetism. Many of the European professors are all his students. He had this idea while he was in Zurich that instead of taking a current through a wire, if you have a lightning bolt, you have electricity that is ultra-fast discharged to the ground, right? And you can create incredible speeds. So the big question is, how can we create an artificial lightning bolt, because we can't put our material there and wait 5 years before a lightning bolt comes along, right? So we have to do something that is under our control. All right. So we know this doesn't work. This technology is too slow. All right. We have these beautiful accelerators at SLAC. And in this case, it's almost like a current that goes through a wire, but it is not a continuous flow of electrons. It is actually a pulsed flow of electrons. You have little bunches of electrons that are kind of grouped, pressed together, and these bunches of electrons whiz down the accelerator with the speed of light. It's almost like a current, right? But it doesn't flow in a wire. It flows in a vacuum. And therefore, it can go with the speed of light. And so how fast this is depends on how much you can compress the number of electrons that create the current. And that we can change. But it is clear we already know that we can compress these bunches so tight that when the other thing, before I come to the final conclusion of this experiment, we also know that when this whizzes down, it is just like a current-carrying wire, and it has a magnetic field around it. In fact, the magnetic field travels with a bunch. And so all we have to do is we have to add a sample. And so this bunch comes down, flies through the sample, and writes a magnetic pattern. Ultra fast. And we can change the time that it writes by making this little bunch longer or shorter. This is an ingenious idea. So the way it really works is, and I can't go into complete detail here, the way it works is that you have a beautiful magnetic field, and you have this sample, and you write a nice pattern here. And as you go away from the electron bunch, as you get further and further away, the magnetic field gets weaker and weaker. That is shown here. And at certain places here, it switches. At this place, originally, all the magnetic magnetization was in this direction. It flips around once. It flips around to the white, then back to the it flips around twice, it flips around 3 times, and so on. So we write a very beautiful pattern of zeros and ones if this process is reliable. Okay? So we can do now this experiment. We put the sample in the beam. We can take a material that we get from one of the magnetic recording companies. But here is a nice picture. This is the biggest magnetic recording head you have ever seen. In fact, it is 2 miles long. This is Freeway 280. And so this bunch of electrons whizzes down the accelerator with the speed of light. And at the end here, which you can't see, we have this sample, and it just goes through the sample. And if you look carefully in my previous view graph, you actually saw that it does go through the sample because it makes a little hole or it melts the sample. So we don't use that area. We do. All right, so this is how we record. And now we can do an experiment. We can do a beautiful experiment because we have the ability to make this bunch long or short. And we didn't have that much time to do this experiment, that we only have 2 points. Of course, in the future, we want to fill in the data. But so we did the first shot, and we took a conventional running of the machine. It has a bunch length that is 3 picoseconds. What does that mean? It's 30 times faster than what a current through a wire can produce, right? 30 times faster. Beautiful. You still get the ones and the zeros. Everything works fine. So all our friends in the magnetic recording technology know if you go only 30 times faster than today, everything will work fine. But now, look at this. Now we really compressed the bunch. And we went 1,000 times faster, right? And look what happens. We do not write, let's take this ring here. That ring is all zeros. It's very well defined. But here, there are some ones, zeros, ones. It does not switch reliably anymore. So there's a speed limit. In fact, now you probably want to know what that speed limit is. I don't know. We don't understand it. So we actually in the future need to understand what happens. How does this pattern form? What limits it? Why doesn't it form in a regular way? And we already have the next experiment lined up. It's going to wait a few years. Oh, before I come to that, I want to just summarize, because that's the end of my talk. I'm going a little over, I'm sorry. I want to just put it all in perspective now. I've told you that the size in computers we understand very well. We are up here somewhere, right? And so if we go smaller and smaller in size, we kind of hit a limit where the magnetic bits, the ones and zeros, will be, in fact, these are atomic spins. They will be all random. The magnetic bit is not stable anymore. We well understand that. On the time scale, we have established with our SLAC experiment now that somehow down here is also a speed limit. So we still have room to grow, but we will run into this fundamental speed limit. We don't understand what it is due to. But so how much do we have to go? In this case, in terms of size, because the bits are not just in one direction, but they are also in, it's a two-dimensional thing, we can shrink one way and the other way. So we have a lot of room to go. We can go a factor of 30 in length, can make it shorter, and we can make a factor of 150 in width shorter. So that's a factor of 5,000. So don't worry. Tomorrow your computers are still, the next few years, everything will be fine. But on the horizon, 10 years from now or so, watch out. Now the speed. What I've shown you is that we have less than a factor of 1,000 to go. We don't really know because we only have one point here. We cannot explore some of this area here because we can, but we have to do that in the future. And we don't really know why it fails. So the experiment that we have up our sleeve to really look at this is, what do you really want to do? What we did before is we took this sample, put the beam through it, it wrote a beautiful pattern, we took it out a few days later, looked at it under a microscope and said, well, this worked and this didn't work. But what we really want to know is when this process happens, when the beam goes through, when the switching occurs, where does it go wrong? Why doesn't it work? And so what do you have to do that? You have to have a technique that can look at ultra small things, and it has to look at it ultra fast. That means you have to be able to take a movie of how does it evolve from an ordered pattern into some random pattern, right? Now this is a movie with incredible speed. And you cannot take it with light because you can't see it with light, so you have to take it with X-rays. And you have to have ultra-fast X-rays that one shot of X-rays will give you a picture how it looks at one point, and a short second later, you see how it evolves. And that is what we have our sleeve. And it's called the Linear Coherent Light Source. This is the next accelerator we're building at SLAC. It's the first X-ray laser in the world. I think Herman Winnick already mentioned it in his talk. It allows us to see the invisible, because we use X-rays, and it allows us to see it ultra fast, so we can take movies. So here is SLAC. This is the 2-mile linear accelerator. We are here today, the auditorium. This is the entryway. This is 280. This is Sand Hill Road. And most of the experiments today are done here at the end of the accelerator. This is where we did the experiment where we put the electron beam through. But what we are doing in the future is we're extending it. We're taking only part of the LINAC, and then we use the electron beam and we convert it into X-rays. Now that's a whole story by itself, but it works. We know how to do that. So out comes this death ray of X-rays. Ultra fast, ultra intense, and we have so many X-rays that with one X-ray burst we can take a picture. So by delaying part of the X-ray beam, making one part go through first and another go through second, we can take a movie. So that's what we want to do. We want to see how it really happens. And here is an artist rendition of what it's going to look like. As I said, it's the first X-ray laser in the world. It is to come in 2008. And we have all these nice buildings planned. And so that's the future. Anyway, in summary, Magnetism, I think I've told you, is an old phenomenon and topic, one of the oldest phenomena of science, actually, of physics. It has many important practical applications: navigation, electricity, wireless communication, medical imaging. It underlies the modern data storage technology. In the future, it may actually replace some of the silicon-based chips. Because magnetic memory is what people call non-volatile, it does not go away when you turn off the power. You can also use in memory applications, or in RAM, you can build magnetic random access memory. This is, for example, something the military is very interested in. Anyway, I have shown you that we are far at the end of magnetism. It remains an exciting research topic. And I think I've also told you that the mystery of magnetism continues. We really don't know everything yet. Now, before I stop, I want to acknowledge a few people. Ann Mueller, who's here, who spent a lot of time helping me with the animations, where the current flows through the wire, and so on. So this is a non-trivial thing, and I thank you very much. If you're scientifically inclined, when I'm working on my book, or if I don't know how things work, I often go to this website, How Stuff Works. It's really great. In fact, everything I told you today, I got off that website. All right. And then, of course, I want to thank my research group. If you're interested in wanting to look at our work, here is my personal website, and this is what my group has put together. And of course, I've given practice talks, and many of my students and associates have given me pointers of, well, I didn't understand this at all. You have to do better. Okay, so thank you very much. All right, let's take a few questions. Maybe I shouldn't take any questions. I might not do the answer.
Questions.
Okay, 3 questions.
More questions outside.
If I don't know the answer, my students will answer it.
The question, conceptually, if you're measuring these ultra-fast magnetic events, how do you record an image that fast? How do you?
You see, when we did our experiment of the SLAC experiment, sending an electron beam through, we did not record. We didn't look at the image while it was forming. It formed, it became stable, and then a day or two later we took the sample out, and then we took it to a microscope, and we saw what image the beam had written. So that is one way of doing it. But I think your question is more with the X-rays, right? Well, that's a tricky question. I mean, the whole experiment becomes complicated because you have to excite the sample and then you have to probe it. And that's what we call pump-probe experiments. So these are very common experiments where you take a sample and you want to measure its response. You excite it with something, and then a short time later with a probe beam, in this case an X-ray beam, to see what has happened. And then you take images as a function of time from when you have excited it to see its evolution as it evolves. This is the concept that you use.
A basic magnetism question, that is something I still don't understand. But if you have a negative and positive pole of magnet, why do they attract? Like what's actually going on there? I mean, I understand the concept of negative and positive forces and attraction of that. But as far as why are they really coming together? What's having those two materials actually pull each other together?
That is an excellent question. And, okay, he asked, if you have a North Pole and a South Pole? Why do they attract? And why does a South Pole and a South Pole repel each other? Okay? Now, this is a tricky question because it actually gets down to the very concept of what makes magnetism, namely the concept of the spin. I mean, we typically accept this as, like Goethe did, as something that is just there in nature. And that is, if we teach this to our kids, we say, well, that's the way it is. But when you really get down to why it is, you have to then look of what causes magnetism. And it comes down to the concept of the spin. And there's a whole bunch of funny phenomena going on with the spin. Namely that in spins, there is a certain, for example, if you have in atoms a certain state that in an atom where an electron is in a certain state and it has a spin up, let's say. There is a fundamental theorem, or, well, I guess I don't know whether you can derive it by first principles. It's called the Pauli principle, that no other electron can be in the same spot with the same spin. If it is in the same spot, it has to be the opposite spin. And so these attraction and repulsion between magnets goes back to the very concept of the spin, of the interaction between spins. And they create magnetic fields. You asked me that question. I'm sorry.
I understand the concept of magnetic field, but why do they actually come together? As far as gravity is concerned, Einstein said there's a picture of space-time. Clearly that's not what's going on with magnetism.
Yeah, so. Of course there is a force, right? So what is the origin of this force, again, comes down to the very concept of the fields that are created by the spins, by the magnetization of a sample. It is actually very complicated.
Thank you.
Maybe after this lecture and I think about it, it will just come to me. but right now I can't give you a better answer. Let's take one in the back there.
There are several metals which are paramagnetic, iron, cobalt, and nickel.
Yes.
And they have unpaired electrons,
Yes.
as you were indicating.
Yes.
But there are lots of other metals that have unpaired electrons, and they're not ferromagnetic.
Yes.
I wondered what the structural reason was. It seems like
Yes.
unpaired electrons are necessary to have.
Again, it comes back down to the concept of the spins, the atomic spins, that in some cases, because like spins don't like each other, they have a repulsion, that in some cases electron clouds are localized on atoms and they align parallel. In some cases, they actually align anti-parallel. Those are antiferromagnets. And in some cases, there is no order. The coupling between the moments on the individual atoms is not well defined. This actually comes out of a very complicated theory that when we try to explain this, we actually have to develop a theory that goes into how the electrons move around in crystals and how they interact electrically and magnetically with each other. It's called band structure theory. And then you can get a picture for it. Many of the naive pictures that we have actually don't work. And this is why magnetism is still such a complicated thing. In fact, the most challenging problem in condensed matter physics today, in all of condensed matter physics, condensed matter is materials physics, is the interaction between charges and spins in a solid. And there are very complicated phenomena that take place. They're called correlated phenomena, correlation effects. And to describe them, we actually don't have a good theory to do it. We can do it in certain cases, but in other cases we can't do it. Again, mystery. It is so complicated. But, I mean, there is a good reason why it's so complicated, right? If you ask how many atoms are in a solid, you can, quadrillions. And so you have to then solve, if you did a calculation, you have to ask, well, how do they all interact? How do all these electrons interact? It's not just 2 electrons. We know how to treat 2 electrons, how to calculate that. But when it comes to 3 or 4 or 5, we already run into problems. So we average most of it out.
I've asked chemists, and I've asked material scientists, and applied physicists, and just about anybody I can think of, and nobody really does seem to know why that's so.
That's correct.
So Goethe was right.
I'm sorry, who? Yeah. Yes.
Joe, everybody, thank you very much. I can see we're going to be a long time. Cookies, drinks, and spot the scientist outside in the lobby.